In the last video, we modeled a parallel plate capacitor with air as a gap. In this lesson, the goal is to model a capacitor, but then with dielectrics in between the plates. Now, the topics to be covered would look at how to use symmetry planes to reduce the computational domain, define different material properties in CST Studio, and also create a capacitor with multiple dielectrics, calculate the capacitance and compare the results. Then use post-processing to just some of it, not all of it. So let's dive in now. Open or recreate the model in the previous exercise. So I already have the model opened. I haven't saved it. I think I should go ahead and save that now. Save it to desktop. Let's see. Capacitor. Yes. So now that is all saved, I'm going to undo. If you remember from the last video, we kind of reduced the domain, the boundary, the background, sorry, the background, so that we have no stray fields. So now I'm going to undo that, and that's by going to this and setting the background back to normal and applying it 1 meters in all 1 meter in all directions. So okay, my system is freezing. So that wasn't my system freezing, it was actually network, and I hope this video continues. If it doesn't, well, it would be a lot of wasted time, but yeah, let's get right into it. So I'm changing this back to 1 meter, applying, so expanding the background. So apply, and yes, delete previous results. Yes, so then I should also undo. So it's like we are starting from the first example with the stray field. So remember what we did to remove the stray fields. First of all, okay, sorry about that. Someone was at the door. So yes, we um, set the boundary condition to magnetic. So we have to undo that, and now it's open again. So we have a space. I think I'll turn off this. It's a bit annoying. Turn off the working plane, yes. So I can have my model now. Oh, where did I keep that? Okay, so open or recreate the model. Now the model is symmetric with respect to YZ, XZ, and XY plane. So if you look at the model, is symmetric to this plane, which is your YZ. So if you should draw a line through the middle, it means you have exactly the same thing on either sides. Then if I should change the view and you look at the XY plane, you also have a symmetry. It just means that if I should use a line to separate this model into two parts, you have exactly the same thing on either side, exactly the same boundary condition and exactly the same geometry. Then the last one is your XZ plane. So if you should look at it also from the top, you have that. If I should draw a line through the middle of this, you also have symmetry, which means you have the same conditions on this side. Now this helps us to simplify our model, and just I'll apply the boundary conditions for the simplification, the symmetry planes for the simplification. So when you notice this kind of symmetry, remember it must be exactly the same model and also the same boundary conditions. If you have a different boundary condition on either side, then you can't apply the your symmetry plane condition, or else you can, but then you would have results that are not correct. So in order to apply the symmetry planes, you go to your simulation tab, and then you go to boundaries, and then you see over here you have symmetry planes. Now when you click on it, you see the different planes that you could apply the symmetry to. So these are mid planes that you could apply symmetry to. So the symmetry condition we have to apply is E normal is equal to 0 at the YZ plane. E normal is equal to, that's the normal electric field, is equal to 0 at the XZ plane, and also the tangential the tangential electric field is equal to xy on the x is equal to 0 on the xy plane. Now, before that, I would show you why we apply this, or should I? Yeah, I'll show it. But then I have to solve the system again. Yeah, we don't have results because I changed everything. So I just run a quick solving. And yes, we have our results now. This is it. Now, if you should look at the electric field, if you should look at the electric field in the YZ plane, so we are looking at the YZ plane, then this is just one slice. But then if you should move it, you have exactly, I think, yeah, kind of exactly the same thing, except for where you have your fringe fields. Now, is that what you notice is that you have no normal component. How should I view this? If you should look at this plane, then you have just tangential components. Now, how you should know if you have normal components is, the trick I use is if I should check on the tangential plane to, remember we are looking at YZ, right? Now the tangential plane to YZ is XY. So if you should look at this, I don't know if I can see the planes. Okay. You really can't see the planes. Okay. But you have that the plane currently in view. Let me change the view so that it will be better to look at. Oh, but then you won't see the arrows. Okay. The slice we currently have on the 2D plot, so your sectional view is normal to X and the face is YZ. So if you should look at the plane tangential to this, so looking at the plane tangential to this, you have two planes tangential to this, and you could look at both of them. So I use three. You see that there are no arrows pointing outside of the plane. This implies that the normal component on the YZ plane, remember this is the YZ plane because you see here YZ. Now the two tangential components to the YZ plane are XZ and XY. So if I should click 3 on my keyboard, then it shows me the XY plane. Now I have to also look at the XZ plane and I use 8 to look at the XZ plane. And then you see that from the YZ plane, there are no arrows sticking out. So this means that your normal component of the electric field, because we are viewing the electric field on this plane, is 0, which is what is here. Now you do exactly the same thing for the XZ plane. I would do that also. So for the XZ plane, your XZ plane should be, the normal to your XZ plane should be your Y direction. So this is what we have. And to view it, I use 8. So you could see that the image also corresponds here. So 8 is like your top view. So what we have is that, oh, 8, yes, we have your XZ plane currently. Now we look at the other two planes and see if we have fields pointing out of the plane. If we have fields pointing out of the plane, then we cannot apply the normal condition. Maybe we would have to see if there's some other symmetries to some other boundary condition that we could apply. We could look at also the H field, H field, yeah, the magnetic field. So if I should look at the XY plane, which is perpendicular to the XZ plane, I hope I don't mix them up. You see that there are no fields pointing out of the plane, and then the last one we have to look at is the YZ plane. So you have that the normal component, there are no normal component pointing out of the plane. So that's how you have that your normal electric field on this plane is 0. Now lastly, I would also show this. We have the XY plane. Now your XY plane, the normal to your XY plane is Z. So we go and change this, the normal to Z. And what you see is that, now let's view the XY plane. XY plane would be, sorry, use 3 to view the XY plane. Now you see the XY plane. From this, you can already see that it's not tangential because you do not have any arrows here. You just have arrows pointing in and out of the screen. I think just either direction. So it's either pointing in on out of the screen. Now, when you look at this, you could already conclude that the tangential field on this plane is 0. But then let's confirm with looking at the other plane. So if we should look at we have to take a look at the x z plane and also the yz plane. So looking at the xz plane should be 6. Now this is yz. So xz plane is 8. Yes. So when you look at the xz plane, you see that the arrows are clearly pointing out of the away inside and away from the plane. That's from the xy plane. And then when you also look at your YZ plane, you also have arrows pointing out. So that's one way to know. But most of the time, with practice, you could easily tell them apart without going through all these processes. This process you could tell which symmetry condition is appropriate for application. So we have this, and then now we move on to apply the um, symmetry planes. So we go to simulation tab, and then we go to boundaries, and under boundaries we have symmetry planes. Now one other thing, we have just E, I think. Oh, this is new. No, we have electric boundary symmetric condition. Et is equal to 0 and ht is equal to 0. But then what we want to apply is E normal is equal to 0. Now in CST, E normal is equal to 0 implies HT is equal to 0. So they are one and the same thing. So your tangential component of your magnetic field is equal to 0 suggests also that the normal component of E is equal to 0. So we apply this to the YZ plane. Yes, I'm correct. Then for the XZ plane, we apply the same. So HT is equal to 0. Then for the XY plane, we have that ET is equal to 0, and we have that here. So we are done with that, and yeah, we delete the results now. Oh, I don't know if you saw that. Now if you should look at this, yes, you see that you now have your boundary conditions just specified for a quarter of the geometry. So for just a quarter of the geometry, so you have that the model is now just a quarter. So because of the symmetry conditions, when you apply your mesh, it's just going to be only this quarter of the geometry is going to be meshed and then mirrored over the other side with the appropriate boundary condition. So that's one use. It reduces the computation, the amount of time using computing for the whole model. You could just compute for just this quarter and then mirror it, and that's okay with the appropriate boundary conditions. If you do not apply the appropriate boundary conditions, then you have unphysical solutions, or maybe the solutions are even physical, but then it's not what you are trying to model. So be careful to always look at the boundary conditions, and even after solving, take a look at the results you have and see if they reflect the physical system that you're actually trying to model. So just some tips. So after that, by knowing the behavior of the field at the symmetry planes, the computational domain could be reduced. Yes, so this is what I just showed. And we are done with this slide. Now, in the simulation tab, click boundaries. So simulation tab, oh, sorry. Yes. In the simulation tab, click on boundaries and then symmetry planes. Oh, okay. I think I was already ahead of myself. So we're already done with this. Now you can see, I'll just click it again just to show. You can see that this corresponds. I didn't know that the slide had this. So you can see that this corresponds to what I just explained. En corresponds to hc is equal to en is equal to 0 corresponds to ht is equal to 0, and then et is equal to 0. We already have that. So moving on to the next slide. Now we have to run the simulation while adaptive mesh refinement is enabled. Now you remember your adaptive mesh from previous the previous tutorial. Adaptive mesh refinement, so it automatically makes your mesh finer and finer, and then with some stopping condition that you have, and then the number of passes, the number of refinements that you want. So let's go ahead and run the simulation. I think hopefully everything is set up and we don't have any trouble. So yeah, we run it and then adaptive mesh refinement, leaving the settings from the previous time. Yes. So remember to run, you click on setup solver and then start. So um yes, so we can view the potential, that is V, and that is potential ES and 6 3. Something, what's wrong? Okay, looking at the wrong plane. So this is one of the planes, but it's not the plane doesn't correspond to this. So what I'll do is I'll go to 2D 3D plot and then section view. I want to view the X plane. Yes, so this is the correct plane. And if you also look at this, you see the model being divided. Maybe I could turn off the plane for a while. So if you want to turn off the plane, you could click on it and deactivate it. So you have just the model. So as you can see, you have just a quarter of it. So it's just a quarter of this and then it's mirrored. And you can also see this in the mesh here. So I mean you could view the mesh view, and then you have this. So it's only viewing the mesh for the model, but then you could also turn on the mesh for the, I hope I can see it here. Bounding box is uh, how does one turn on the mesh for the bounding box? Mouse control, change view, orthographic reset. Okay, not very important. Yes, background, yes. Got it. So the background mesh, now when you turn the mesh for the background, you see the whole background and the mesh, but then you can view just a section of it. So cutting plane, viewing X, and yes, this is it. My settings, I think I can make it not wireframe, but then maybe make it transparent. Because now it's colored. So oh, change view, orthographic, no, sectional view, mouse control, no, visibility, wireframe, no, bounding box, yes. Should I? Yeah. Okay, not very important. It's just part of the settings. So if you see, yeah, if you see something like, oh, I think I remember, it's part of my own default settings. I think so, but it's not very important. You see already, kind of, sort of, the mesh 6. Yes, you could view the mesh, and then it's kind of, you see these symmetry lines. So it's the same mesh mirrored over the symmetry lines that is plotted. So back to the potential, and yes, this is it. But then what's wrong? I think something is not right here. I think something is not right. What did I do? Section. Okay, so currently it's just cutting plane, but then no field values. So fields on plane, this is what I'm supposed to click exactly. So if you have just, you could have just a sectional view, but the fields are not displayed on the plane. So it just kind of gives a zero. It makes the field zero everywhere, but then you would have to click fields on plane. You could disable this first and then just click fields on plane. Then it automatically selects the cutting plane and then adds the fields to it. So we have the same thing as we have here. And then we've actually spent less time. You could view that. I won't do that now, but then you could view the time elapsed for the simulation in the log file. So you go to your home tab. Oh, I always end up double clicking this. You go to your home tab. When you double click, it collapses, and then you can only view it once like this. But then if you ever double click it and then you want to bring it back, just double click again, and then it brings out the ribbon. So to view the log file, You just go and then click on log file. Then you see electrostatic solver. It has the symmetry planes, it has the boundary conditions, and it has some warnings. Okay, this software is licensed for educational use. Then the solver order, it has so much information, and then you can see the total time elapsed. So for this, it's just 1 second used for the simulation of this. And then I mean, then you could compare the time. We didn't look at the solver time for the full model, but for this one is 1 second, so you could also check. And one thing I saw just now is the desired accuracy, which we set 1e2 minus 6, but then this is the accuracy of the solution 1e2 minus 15, which is better than what we set. So over to the next task. Now, we just dealt with using symmetry planes to reduce the computational domain and also save time for ourselves. I mean, this is a very small problem, so it may not really make much of a difference, but then bigger models, you would need all the symmetry planes you can get, trust me. So we've explored the symmetry planes. Now we look at um, creating dielectrics. So dielectrics are just blocks. So we've looked at modeling blocks. We model the plates as blocks. Now we'll do the same with the dielectrics. The only difference, or the only thing we would be doing, is we would be assigning material and defining new material for the dielectrics. So we have the permittivity of the dielectric, of the three dielectrics here. So we go over to model. Let me see if there's the okay. I think first of all, let me look ahead. Okay, there's a slide on the modeling. So first of all, we could do any of them before each other. So in the slide, you have that the materials are defined before the dielectrics are modeled, but then you could also model the dielectrics as blocks, then define the material and change the material. So let's just follow the tutorial. So we have in the navigation tree, this is your navigation tree. Click on materials and then right click on materials. So if you should click the drop down, you see the materials that are already present in the model. Now to create new materials, you just right click. So this is right clicking and then new material. Now you have to create 3 new materials. So I'll call this material 1, material 2, material 3, just for simplicity. Now you have the type of material. Normal is not perfect electric conductor. You could define other materials, but then this is normal. And let me bring this close to here. For the first material, the epsilon, the relative permittivity is 1. I think I'm seeing that clearly. Yes. So that's for material 1. And that corresponds to, no, it's 10, not 1. What did I say? Navigation tree. Okay, 10, 5, and 20. Okay. So I've already created the material, but then I could go and right click, and then you could go to change, not change material folder, but edit material properties. So you could edit it to be 10. So we need to define with epsilon 10, and then we could also change the color. So I could change material 1 to match this color. It's already the color. So and then okay, then I do the same thing, right click, new material, material 2 with epsilon of, just trying to match the tutorial here, epsilon of 5, and then I could change the color to, I think this is some kind of yellow. Let's see. Yes, or maybe it's a bit dark. Could define custom color, but I think this is okay. So change the epsilon to 5, and then lastly we have purple. Yes, and the epsilon is 20. Yes, so we've defined the 3 materials that we need. Now we go over to modeling the dielectrics. So now back to 3D view. I think in older CST versions you don't have it like this. So if you want to go back to 3D view, you just have to click on component. But for 2022, for some reasons, it doesn't automatically switch. So if you're using 2022, then maybe you just have to click on 3D. So you have schematic, your results. You can easily switch between your results and your 3D view. But earlier versions, you just click on components and then it automatically switches. Now, to model the dielectrics, go back to modeling and then break and then escape. Then the first dielectric, we just have to match this minus 0.5, 0 minus 0.5 and 0.5 and then minus 0.05 and 0.05. Now we could preview and then this is the preview. So let's see the other section. Yes, 6, not 6.3, not 3.8. So I'm looking at it now from the top. So I have the first material and then the material would be, so I'm going to make it match this. So material 1. So this is material 1. You just click on material, the drop down, and then you see all the materials in the model, in the present model. So material 1, then preview, then okay. Yeah, delete the current results. We don't need it. So we have this. Then for the second one, we have, you click on brick, then escape, and then we have I think this is 0.5. I have to because it's kind of tiny for me, but then you should have the slide, so I think it should be okay. Oh, but I guess it's not very tiny. Minus 0.5, 0.5, 0 and 0.05. And I'll preview it. Yes. So this should be material 2 or material 3. I mean, depending on how you're looking at it, okay. You're looking at it like this. So this should be material 3. And okay. I'm just trying to match everything just so that when we see the plots, the graph, then we have exactly the same thing and not different plots. So yes, okay. And we have that. And then lastly, we need the third dielectric material. So brick, escape. Then you have this. Oh, I think I made a boo boo. Yes. We have 0, 0.5, minus 0.5, 0.5, and 0, then preview. Yes. And then the material is material 2. That's all we have left. So we have a model looking like this. Now, mind you, these dimensions that are written here in the tutorial, you could also get them from here. And then since your model is positioned, or our model is positioned at the 0, 0, then you know how to get the offset from your 0, 0, and then that's how these numbers were gotten from this model. It's given here. You could um get the numbers yourself. So the next step, define background space and boundary conditions such that the electric field exists only between the plate capacitors. Now remember this, that what we did last time, and this is to avoid fringe fields. Now remember that what we did the last time was to apply appropriate boundary conditions. First of all, we reduce the space. So we reduce the background space, and we reduce it by going to simulation background, and then that's 0. So we do not want any added space, and then apply in all directions. Then apply. So our background doesn't vanish, but it's just glued to our model. No, you can't really see it. Okay. Maybe if I should. Okay, it's there. Trust me on this one. It's there. So this is what we have currently, but then that's not all. Remember, we had to apply some boundary conditions, which is the normal electric field to be zero. We do not want any stray fields out of this domain. So we go to boundaries and we go to magnetic. And okay, what I'm seeing now is, let's see. Now let's observe this. Now we still have our symmetry planes. We still have our symmetry planes activated, but then you look at this model and ask if it is symmetric. Now you see that first of all, let's look at the XZ plane. Is this model symmetric in the XZ plane? The answer is no, because we have a different dielectric material on this side than on this side, right? And then if we should look at it from this plane, then if we should draw a line through this, we have a different material on the left and a different material on the right. So it is not symmetric in this plane. Now let's look at the last plane. I think that should be 3. Now if I should draw a line through the center, is it symmetric? And the answer is no, it is not symmetric over this, because if I should draw um a center line from this, then we do not have exactly the same thing. Now the plane in which it is symmetric is this. Oh, I think I made it. No, 6. If I should draw a line through this, then this is the xy plane. Then this is 8. If I should draw a line like this, okay, this would still be exactly the same line as the other line I drew. Now the symmetric plane would be this plane, and this plane is xz plane. Yes, is this plane, because now observe that if I should draw a line 6 3, yes, if I should draw a line, a center line here, then you have that I have exactly the same materials both up and down, because you have that the electric on each cross section is exactly the same. So maybe I could also demonstrate that by going to um sectional view. Yes, cutting plane. Now let's look at this plane. One thing you could also do is yeah, I have to slide this now. So this is your x plane, and you see that okay, we have the same materials, but then throughout it changes. Now you could now look at your y plane. Now this is your y plane, and remember your y plane is normal to your x z plane. Now let's look at the changes. First of all, I would okay out of this so that we see it clearly. Now watch the y plane. Now if I should go from top to bottom, you see that you have exactly the same material combination in also cross sectional areas. Then let's look at for z. So there's symmetry in y. Now let's look at for z. This is what we have in the z. Now okay, if I slide backwards, I have almost exactly the same thing. Then there's no there's a different material. Then we look at this, you also have different materials. So it is only symmetric in the xz plane, and your y is normal to the xz plane, so it's only symmetric in the xz plane. So this for this reason, I think this question comes out later. But okay, I think we'll get there if we don't. But for now, I will just solve it without any symmetry boundary condition. So I'll remove everything for now. I think the question comes later if I remember correctly. So okay, and then no, not done. I now have to apply my magnetic boundary condition. It's already applied, but then if it wasn't applied, you'd apply your magnetic boundary condition, and this is to remove all stray fields. So that's what we're told. Now define the space such that the electric field exists only between the plate capacitors, which is the assumption for which you have all these formulas. These are C1, C2, C3, and C total. So we are done, and it's currently showing sectional view. I don't want that, so I want the whole geometry. So we are done. Run the simulation, calculate the energy, calculate the capacitance of the capacitor, just like we did the last time. So if I should go to simulation solver setup, I'm leaving out adaptive mesh refinement, so I'll start it. Now that was quick. Now what you have, just like in the previous tutorial, you have your electric field energy. So you have electric field energy reported in different components, right? So you have your solid, and the components are the dielectrics. So your solid 3, solid 4, and solid 5. Let's look at solid 3. So cyan, that's your cyan dielectric. Then you have solid 4, which is your purple dielectric, and then you have solid 5, which is the yellow. So you have the energy, the electric field energy inside each of these components. And with this, you can use this formula. Now, where's that formula? Where's that formula? No, not this one. This is the old slide. Oh boy, I saw that just now. I think I could copy from the old slide. Yes. Now you could use this formula to solve for the capacitor in each of the dielectrics, and then compare your answer with the analytical solution. So your this would be U1 is equal to 1 half C1 V square, since it's the same potential difference across each of the capacitors. And then you compare it with this answer here. I won't be doing that here. Then the total energy is what you, if you should use the total energy in this formula, you substitute, then you have the total capacitance, which is this, and then compare it also to the solution. If the answers do not tally, then something is wrong with the simulation. Now plot the electric field along the z-axis at xy is equal to 0.25 meters and 0, and xy is equal to minus 0.25 meters and 0. Now this is post-processing. We have our fields, we have our potential, we have everything we need from this model, but then maybe we want to make some plots. Maybe we want to observe how the field changes along a particular axis, which is what this is. All of those come into post-processing, and then you have a separate post-processing tab for that. So if you should click on the post-processing tab, you click on templates. Okay, let me go with the tutorial. In the post-processing tab, which is this, click on result templates, which is this, and then you have this popping up. Now click on result templates, 2D and 3D field results. Now if you need anything with your field result, your 2D and your 3D field results, you click on this, then you can now and then evaluate field in arbitrary coordinates. So when you click on this, it changes the options you have available here. So just as a demonstration, if I should click on general 1D, you have a different set of options. If you want to post-process your 2D and 3D fields, you click on it, then you click on this drop down, and then you have different options. Now what are we supposed to select? Evaluate field in arbitrary coordinates. So when we click on that, you have another pop-up, which is like this. Now what do we want to do? We want to plot the electric field along the z axis. Now we could calculate 0D, we could calculate, evaluate the electric field at a point, we could calculate it on a line. 2D, we could calculate it on an area or a face, and then 3D, we calculate the electric field or the minimum, maximum, integral, or the volume in 3D. But then we want on a line, so 1D coordinate. And what's the direction? On the z-axis. So we change this to the z-axis, and then what he said, x comma y is equal to 0.25 comma 0. So this is x, 0.25 comma y 0. So this is the first. We are required to plot 2. So this is the first, and then what do we want to plot? The electric field. Now you go to please enter result name or browse for it. So we browse for the result, the electric field, that is what we want to plot. So we click on that and okay. So we have our result. Now what do we want to plot? Plot the electric field along the z-axis. It wasn't specified if we wanted to plot the absolute component or the Z or the Y or the X. So I'll just leave it as absolute. And then the real part, you could also change it to magnitude. I don't think this doesn't have a complex part. So the real part should be the magnitude. And that's it for the first. So I click on OK. So I have for the first line, now I could duplicate by clicking this or do exactly the same thing. So I'll just duplicate. And then I have settings. So when I duplicate, I could either double click to bring up this um, pop up, or I could just click on settings. So we have exactly the same thing, electric field along the Z, but then the axis, the x comma y is different. So one on minus 0.25 comma 0, then the whole of the z axis. So that's it. And then we can evaluate both of them. So I can evaluate all, or I can evaluate them individually. Let me evaluate all. So once you click on that, it runs and then it's done. Now to view our results, you come down to tables. Let me expand this a bit. You come down to tables, expand it, then 1D results, you expand it, and then you have electric field, which is the first one. So this is what you have. Oh, I'm a bit ahead of myself again. So the first one, this is what you have. So it's kind of reflected, but yeah, it depends on how we modeled it. I think we took the top view instead of the bottom view, or although we try to make it match, but then you see that it's one and the same plot. So this is for 0.25 comma 0, which corresponds to the first. Okay, maybe I should label it. So I'll go back to this, and then just so you see that is exactly the same thing. So this is 0.25 comma 0. So I would label this E field absolute Z 0. I hope I can use a point. Yes. And 0. Yes. And then I label this minus 0.25 comma 0, and I evaluate again. Yes. And then I have the plot, which is the same as this. So for 0.25 comma 0, that's this. And then for the second one, I have this, which is what we are looking for. I could also plot both of them together by holding down control, selecting one, holding down control, and selecting the other one. So you have both of them together. So I think that was it for this tutorial. Now the checking of your result would be from in this slide. So you check that your capacitance for each of the dielectrics is equal to the calculated value from the numerical simulation. So I think that's that, and then you are supposed to create this model without any stray field. Now be mindful of the keywords without any stray field, so you know that you're supposed to apply your ht is equal to 0 on the background. So yes, I think that was that for this tutorial, and yeah, see you in the next tutorial.